Okay, so today's class. Last time we had class 1, we were looking at polynomial division. So essentially we had two polynomials that we had to divide against each other, and what I said at the end of that lesson was that it would lead into helping us solve polynomials in a more effective way than we otherwise would be able to. In fact, we did kind of grind through things quite quickly last lesson, so I was able to at least introduce this stuff of remainder and factor theorem. We'll dive into it again, just for anyone this is new to, and then we'll get into some questions, essentially. So, remainder theorem. When we looked at doing polynomial division, we understood that this was quite a lengthy process. It was a matter of grabbing the two leading terms, dividing them, multiply through, do a subtraction, rinse, repeat over and over again until you get your polynomial down to the quotient and remainder portion. If all you care about is the remainder after division, then what you can do is shortcut that entire process with an equation instead. So we have it here. The remainder is the same thing as f of negative b over a, where f of x is the polynomial. So in this case, it'd be this cubic here. And the negative b and a are going to come from whatever the linear is that you're dividing by, where a is the coefficient on the x and b is the constant for the linear. So how's that work? Well, it's basically just plug and play at that point. So if we want to find the remainder after dividing our polynomial by this linear, first things first, figure out what a and b are. A, coefficient of the x, so that's just going to be 1, and b, the constant, so that's going to be negative 2. Nice and easy. To actually get our remainder, we just need to sub both of those into our f of x, which is the cubic. Just don't forget this is a negative b, so even though it's already negative, you double negative it. So you put it in the spot where b is, and the negative essentially doubles up, at least in this case, because it was already negative. That's going to simplify to f of 2, and well, pretty much anyone can do f of 2. It just means sub 2 into all of those x spots, and then simplify from there. Whatever the result is the remainder after division. All we were really doing is subbing into a function and solving. Any questions so far? Easy. Okay, so why do we care about any of that? Well, one of the things it can help us do is solve unknowns in a function. So in this case, we have not just x in our function, but also k as well. One of the key pieces of information we're told is that the remainder is 17, specifically when divided by x minus 3. We've got to use that information to find k. So what do we do from there? Well, again, it's just going to be remainder theorem related stuff. So figure out what your a and b are. In this case, a is going to be 1 and b is going to be negative 3. And we're going to sub that into our f of x. Now, here's the other thing. In the previous example, we just subbed it in, and then whatever we got at the end was our answer. Because we have k involved, we do actually have to figure out what's going to go on the other side of our equal sign. That's going to be where the remainder information comes from. We're told the result already is going to be 17. Whereas in the previous example over here, we weren't told anything about that. We had to find the remainder. So essentially, pretty much anytime you're learning an equation of some sort, that equation can be multi-purpose. You can rearrange the terms in that equation as necessary to solve any of the things involved. Like for instance, you could solve for the remainder, you could solve for b, you could solve for a, depending on what information is given to you. Usually you'll get 3 of, how many have we got? 1, 2, 3. Yeah, usually you get 2 and you'll have to solve the third one. That's one minor application of remainder theorem. More so in textbook stuff. We definitely don't see this in exams, very rarely. I can't even think of a question where it has been in an exam. It shows up in textbooks, and because of that, it might show up in your SAC, because usually teachers they'll base stuff off of the exam, sure, but they'll also look at the textbook stuff that's relevant as well and base it off of that. So, what's this got to do with solving polynomials? Well, if we remember the definition of a factor, it's simply just that when you divide the two terms together, you get a result of 0. As far as remainder, you get a remainder of 0. That is to say, it is perfectly divisible, right? Like 2 is a factor of 4 because there's no remainder left after dividing. So what that can be used for is to find factors of polynomials. So essentially saying if our remainder theorem comes out to being 0, we can actually prove that some linear is a factor of our function, whatever our polynomial is. So for instance, prove that x plus 1 is a factor, very typical textbook question. Well, this is our linear, so we've got to get our negative b and our a from that. Shove that into the function. If we get a 0, which we do after simplification, that means we have found a factor. Why is that important? Well, when you find a factor, when you do the polynomial division approach, you can now use that factor and know ahead of time that whatever I get up here would also therefore be a factor. You're essentially splitting this cubic into a linear and a quadratic. Having done that, you get this statement here, which we should be familiar with from polynomial division. If not, for those who are seeing this for the first time, it's basically dividing this cubic by this linear gets you this result. But you can repurpose that equation. This is a denominator, and so it can be multiplied across the other side. So instead of having this whole cubic and trying to solve that, which there are no real generic ways of doing that, you can instead use null factor law, because you've now got a product of two factors, nothing else involved. It's just one thing multiplied by another. And so you can just solve this otherwise unsolvable cubic simply by using a bit of factorization and then null factor law. That's the application of it, anyway. Any questions as to any of that so far? Okay. Now, the example I gave was pretty simple. It was just prove that this is a factor. That's not so helpful for solving because, well, we kind of already know it's a factor. Why would I bother trying to prove it? More commonly, you'll be given just, here's a polynomial, it equals 0, solve it. Good luck. How do we actually get our factors without any additional information? What we do is we look at that last term at the very end, that plus 6. What we're essentially going to now do is make a list of all the factors of that last term, the constant specifically. So that's going to be your plus minus 1, 2, 3, and 6. All those are factor pairs of 6. Then what you do from there is you simply just test each of these individually until you get 0. And so yeah, you start with the easiest ones and work your way up to the hardest ones. That's a lot of substitution. And so what tends to be the case is you choose the easiest ones first to make sure the amount of work you're putting in is more efficient because it's faster, but doubly so because even assessors also understand that, hey, this takes a lot of time. I don't want you guys, or the assessor will think, I don't want you guys spending too much time on this one question because I don't want to give it that many marks. It's only one concept. So they'll just pick one of the earlier ones anyway, just to make life easier. In fact, I think I ripped this one straight from the book, and sure enough, the very first thing you would have tested, which would be the positive 1, that's going to come out to be 0. If for whatever reason you chose the negative 1, you would have gotten 8. That is obviously not 0, so we did not get a factor. So step 1 of this is list all the factors of this, the last term, and then test them in order of easiest to the hardest until you get a 0. That's step 1 in the procedure. What do you do after you have that? We looked at a simple case, and probably that'll be the only case we look at because the harder version is so rarely tested that it's almost not worth looking at. But basically, in cases such as this, the A term will always be considered 1. That's the only possible outcome for it. I'll give a brief reason why. It's because technically speaking, the A factors are taken from this leading x cubed, right? This has a coefficient of 1, so the only factors of it are 1. If you had additional numbers, like even this, for instance, you would now have 2 and 1 as possible numbers for your A. Don't worry about it. that's more so if you were curious as to why we're choosing a equals 1. All you really need to care about is that you're going to guarantee that a is 1 in this case. The reason why you need to do that is because when you're testing integers and then comparing that directly to the factor theorem, you need to figure out, well, hang on a minute, I've got two variables in here, what do I do? You set a equals 1, that means the only thing left over is comparing negative b to 1. Those things must be the same. That's going to get you b equals negative 1, and well, you have your a equals 1, you have your b equals negative 1, you have thus found your factor. Then, as I said, you can now use that factor to polynomial divide, get your other factor, and then simplify. So, in order, list the factors of this, shove them into f of x until you get 0, use that to figure out your linear, and then sometimes that's all that'll be required. The question might then ask you to solve, in which case you then go through the polynomial division process, and then null factor law. Lots of steps, which is why this is very rarely in an exam or a SAC. Might be in a SAC if it's a limited scope SAC. If it's only doing like 1 or 2 topics, then yeah, they could spend some time on this. But if you think about like all the steps that are involved in that, so you got step 1, which is this. It's kind of like a half step, really. It's more so combined into that. So you got step 1 there. Step 2, get your linear. Step 3, a full polynomial divide. Step 4, a null factor law. That should be a minimum of 4 marks if it shows up in an exam or SAC. And I don't think they want to give that many marks for a single concept, so that's why they typically won't show up. But anyway, that's the idea. That's pretty much all we'll be looking at for today, actually. What like remainder and factor theorem are and their applications, of which there are a few. So any questions on what we've covered so far before we get into textbook stuff? Cool. Okay, so what I'll do from here is I'll grab out some classwork stuff. We'll work on stuff together, but it'll be mainly so that when you leave the class, you'll have something to follow up on. Okay, so I think that's that. Cool. What I'm sending in the chat are the relevant questions in the textbooks for what we're covering today, the remainder and factor theorem stuff. In the Cambridge book, that's going to take you through 6C and 6D. If for whatever reason you're not doing Cambridge book, then this document also shows you where to get stuff done in the Jacaranda as well, which, now that I'm thinking about it, I should probably also link as well. Let me grab a copy of that. Remainder and factor theorem. There we go. Cool. All right, let's give it a shot. So you guys have got all of that now. This chapter does go through a few more things. So much of them are so rare that it's almost just not worth touching on unless your school wants to touch on it. Right. So, if you are learning this stuff in your curriculum, let me know. I will touch on it here. But so few schools actually do that it just kind of seems like wasted work if you're not actually going to use it. But okay, let's give this a shot now. So we're now going to be working out of the other camera. So for anyone who is joining late, if you hop back to the meeting, the regular meeting window, what I'll do is get you to pin the camera that's looking at a notebook, because I'm going to start working out of that. Or I guess we are going to start working out of that. So let's get some questions done. Okay, so it's telling us without dividing, find the remainder after division. Cool. So we got our function, which is in this case x cubed minus x squared. Oh, come on, focus camera. Maybe I just finished writing and it'll focus itself. Minus 3x plus 1 after dividing by x minus 1. We want to find the remainder after division without going through the whole polynomial division process. Who wants to take a stab at it? Once it showed, there we go, finally. I'll leave the notes up on the screen share as well, if you would like to do it that way. Otherwise, you've also got the downloads as well, if you want to have it on your own separate screen. How could we get the remainder after division without actually dividing? I don't need a final answer. Could just be theoretically what you might go about doing. You got two options right in front of you. If you guess one of them, you got a 50-50 shot. If you have a look at the screen share, you've got a decision between using the remainder theorem and the factor theorem. What do you think is going to be relevant?
The factor theorem.
Factor theorem, okay. Yeah, so factor theorem is sort of like an application on the remainder theorem. It's specifically when the remainder after division is equaling 0. So we would use a factor theorem if we're trying to prove that x minus 1 is a factor. I know we didn't really look at the actual question in the textbook, but this one said specifically find the remainder, whereas the factor theorem is assuming the remainder will already be 0. The remainder theorem is used to find whatever it might end up being. So thanks anyway for contributing. 50-50, no worries. Yeah, so we're just going to use the remainder theorem here, which means we need our function f of x, we need negative b, and we need a. Easiest one's probably going to be f of x. What is f of x in this scenario? When a polynomial f of x is divided by a linear ax plus b. Again, it's kind of a 50-50 here. One of them's got to be the polynomial, the other's got to be the linear. Cool, okay. F of x is going to be the cubic, right? So basically any sequence of x to the power of something terms would be considered the polynomial in this case. So this is f of x. The linear, well, we should all be familiar with what a linear is. That's just this bit over here. That's your ax plus b. So essentially that means ax plus b is the same thing as x minus 1. All right, so we're just directly comparing the numbers and letters there. F of x, I won't bother writing that one out again, it's already there. Ax plus b is directly comparable to x minus 1. What are a and b going to be in that case?
A is 1 and B is negative 1.
Perfect. Yeah, a is 1, b is negative 1. Absolutely right. Nice. So we know what f of x is, we know what a is, we know what b is. All we got to do now is figure out what is f of negative b over a. How do we go about doing that?
Now it's going to be negative 1, so it will just be 1 over 1.
Yep, negative 1 over 1. Yep, which is
just 1.
f of 1. Nice. So we know it's f of 1. That will give us our remainder. How do we now do f of 1?
We substitute it into the cubic.
Sub in the cubic, absolutely. So 1 cubed is 1, 1 squared is 1, 3 times 1, so that's the -3 there, plus 1, cool. These are going to cancel, 1 minus 3, minus 2. That is our remainder. That's the final answer. So if we have a look back at the screen share, without dividing, find the remainder after division. We have found the remainder without dividing. We use the remainder theorem. Awesome. Anything to clarify further about how that has worked? Cool. There's a bunch of those to practice. We did one of them. Do we want to have a look at another one that's the same, or do we want to move on to a question that's a bit different?
I don't mind a different question.
Different question? Sure. Okay. So as long as you're relatively confident enough to be able to do these on your own, I guess is what I'm guessing at. What I'm getting at, rather. So, okay, next one up. So in this case, we're trying to find A. That was example 2. Yeah, that's this example in the notes here. So we can see we have a cubic again, but it also has another coefficient A involved. And the key information we're given to solve this question is that the remainder is equal to -3 when we're dividing by x minus 2. So I'll begin writing that down. In the meantime, let's have a think about how we might solve this question in particular. You can also use the notes in my the notes in the chat if you would like to refer to something as you think. A little bit different, but it's still asking about remainder related stuff. So all of these questions are still going to use the same basic equation of the remainder theorem in some way. Question now is how we might go about doing that.
Would we sub in 2, and then instead of it equaling 0, we'll equal -3, and then solve for A?
That's sounding pretty good. Let me just double check real quick. So we're going to have A equals 1 from this coefficient. We're going to have B equals -2. F of negative B over A would therefore be -2 over 1. So yes, 2. That'll be right. Yeah, so we're doing F of 2, and as you said, equating it to -3 because we know ahead of time the remainder is -3. So, subbing in 2, we're going to get 2 cubed, which is 8, plus A times 2 squared, so 4, plus 3 times 2 for 6, minus 5, equals -3. I mean, at this point, this isn't anything anyone's not seen before. This is effectively just linear. You've got one letter left, everything else is numbers. We're just simplifying everything down. 8 plus 4a plus 6 minus 5 equals -3. That can become a 1 now. Plus 4a plus 8. 8 and 1 is 9. Chuck it over there. We're going to have -12 is 4a. A equals -3. Cool. So unless I did something stupid with my simplification there, that's the gist of it. Going ahead and solving for the final letter. Anything to clarify further about those kinds of questions? Cool. All right, next up, question 3. Without dividing, show the first polynomial is exactly divisible by the second polynomial. So this needs us to be a bit more familiar with our definitions. What does it mean for something to be exactly divisible? I'll start writing it out. In the meantime, have a think about what we might do to prove it. I did kind of just give it away actually when I wrote it down. Oops, I used different wording, which might be a bit more easier to understand. Uh-oh. Well, let's hear it anyway. How might we go about doing this?
We could do the negative b over a again,
Yep.
and then sub in the 1 and show that it's got no remainders.
Yeah, that's it. So prove that it's 0. Absolutely. It's an application of the remainder theorem. We specifically refer to that as a factor theorem, but it's literally just the same thing. They're both the same. So yeah, it's going to be 1 because we have a equals 1, b equals negative 1. The f of negative b over a is going to condense down to f of 1, which we want to prove is equal to 0. As a slight nuance, I probably, in my working out, wouldn't immediately make it equal 0. I would just sub it in, and then when my final answer becomes 0, I would say, therefore, we have made a factor. Just a small nuance on how you might actually write your answer in an exam or SAC scenario. But yeah, 1 cubed is 1, 1 squared is 1, x is 1. Hang on, what? Did I write this down wrong? I did. That should be a minus. 1 minus 1 plus 1 minus 1. Look, we can already see that's going to be 0. And so you might then do a therefore x minus 1 is factor. That'd be some final statement you would give, because any of these show that questions, you get to the answer and then you want to have some sort of statement that says, hey, this therefore means that I've proven what I need to prove. That's how you solve those questions. Cool. Question 4 is basically the same sort of idea. It's kind of joining both of those things together. Find m if it's exactly divisible. So again, you're just making it equal to 0 because exactly divisible is factor theorem. I don't think we probably need to go through that unless you guys want me to. The more important thing to start touching on would be the question 5 stuff. I'll pick the ones that don't need rational root theorem, which is the whole what if we have a more complicated number out here. And as I said before, we'll touch on that only if you guys are actually looking at it in school, because so few schools do. Okay, so it's a free-form question. They're just asking us to factorize however we know how to factorize, which may or may not require us to use the factor theorem. Factor theorem will always work, but there are other techniques that you guys would have learned from quadratics, for instance, that can be used to potentially factorize these as well. So I'll start writing out 5b specifically. Let's see how we go. X cubed plus 3x squared plus 3x plus 1. And the statement is just to factorize it however we can. If you know another method, by all means, let me know. Otherwise, the notes also cover this as well. I'll have the relevant bit up on the screen share as well. That should help us start by figuring out where to where to start. Any ideas on what the first thing might be?
We look at our last term and it's just one, so but we look at the factors that go into that, so plus and minus one.
That's it.
And
Yep. And then you were going to say?
And then sub it into the equation and see which one goes in perfectly to equal 0.
Yeah, correct. So you want to see which of these. Could be both, actually. But we only need one of them to work. So let's see. So 1 cubed is 1, 3 times 1 is 3, 3 times 1 is also 3. This is all pluses, not going to work. We don't even have to bother finishing that one off. Negative 1 cubed is negative 1. Negative cancels to positive because of the square, so that's 3. That's going to be negative 3. Positive 1 cancels, cancels. Look at that. So we figured out that negative 1 is the correct number to sub in to get 0. This is the trickier part now, which is how do we now use that to take us to the next stage? That'll be this bit on the screen share.
We negative 1, we put it into the what do I do? We
Right? I think you're on it. A wrong guess is still fine.
I know, like, I know now we're going to divide by x plus 1, but like I don't know.
Okay, so you know how to convert it, but you don't know
Yeah.
what the yep. Okay, so that's fair. You will get to x plus 1 from this. The theory behind it is you have this statement f of negative 1 equals 0, and you have the equivalent statement that f of negative b over a equals 0. I don't know why I did an equal sign there. F of negative b over a equals 0. And we can see a lot of similarities between these two things, namely that the only difference being what's in the brackets. And so because the whole point of doing this is to use our factor theorem, we can therefore say from comparison that negative 1 is equal to negative b over a. Because we have the simple example, the only possible values for a is 1. So this now simplifies down to negative 1 equals negative b equals 1. We can also write a equals 1, so our linear ax plus b can only be x plus 1, which is what you said it would end up being. It's a fair point not to understand where that came from, because before I started tutoring, I also just kind of took it for granted, and I was like, oh, you just flip the number, and that's it. This is the reason why. You don't need to know the reason why, but I guess it's kind of nice, just in case. Yeah, so was that all I was asked for? No, I said factorize. So we're done. We found a factor, but we still got this big polynomial, and we need to figure out, okay, what does x plus 1 actually help us do with factorizing this big old polynomial?
sorry, were you asking what x plus 1? Yeah. When we divide the polynomial by x plus 1, we'll get our equation and the factorized equation and what remainders or.
Yeah, precisely. So what you're getting at there is we use it for polynomial division. Whatever comes up at the top, that's referred to as the quotient, by the way. That's just a key term, just in case it shows up in. It has actually shown up in a multi before. They've said find the quotient, and I'm like, oh shit, what's the quotient again? That's what they mean by that. Yeah. So polynomial division, it's a fairly long thing. Do you need to revise all the steps involved in that, or do you want me to just sort of blitz through a division?
You can blitz through it.
Cool. Okay. So we got our x plus 1 here. Then we got, actually I should probably just look at the screen share instead. We've got x cubed plus 3x squared plus 3x plus 1. Okay, leading terms, x cubed divided by x is x squared. Multiply back through, getting us that. Subtract, that's going to get us a 0 there. 3x squared minus x squared is 2x squared. Everything else is going to drop down. Then we start again. 2x squared divided by x is 2x. Multiply back through gets you 2x squared plus 2x. Subtract. This will always cancel to 0. 3x minus 2x is x. And at this stage, I don't really need to complete it anymore because I know it's going to come out to 0. That was the whole point of figuring out if it's a factor or not. But just for the sake of completion, we can see that this subtraction is going to end up with zeros there. So we've turned our cubic into this and that. As far as completing the factorization, there's only one thing left to do. I know I wrote that pretty fast, so I'll let you guys finish up with the work solution there. And then yeah, let's finish it off. What would be the final thing that we have to write out?
Now we factorize what we got as the quotient.
Yeah, so what does that mean? Like what I write as my final answer for this question?
X plus 1 times x squared plus 2x plus 1.
Sounds pretty good to me. Yeah, that should be it. Now, that'll be, the result of the polynomial division. Worth pointing out, quadratics can also be factorized sometimes. This one looks like it can be as well. How might we factorize? Because when it says factorize, you want to go all the way with factorization. So just keep in mind that sometimes, once you do get to this stage, you might also then have to do another bit left. But quadratics is probably a bit more familiar to everyone here, so how might we factorize that one? Fun fact, you could actually use the factor theorem on the quadratic as well, because it is technically a polynomial, but there's definitely better and nicer ways. Need a refresher on quadratic factorization?
No, like I know what to do, but I don't know like the theory and like what
Okay.
it's called.
Well, what do you get as a result then?
Yeah, it factors down to x plus 1 squared. So I think it's just all x plus 1 cubed.
That's exactly right. Yeah. So to explain a bit about like how you got there, you're essentially just doing it add together times together. What numbers multiply to give 1 and add to give 2? You got 1 and 1, which is where you get your x plus 1, and well, in this case, this is literally all just x plus 1 up until cubed, which is kind of funny that that comes out to be that way. That is fully factorizing there in a nutshell. That's as far as this chapter goes, as far as its question sequence. It'll just get you to factorize, and then that's it. Then there is an entire chapter dedicated to saying, now what happens if I say this equals 0? Well, you're going to follow the exact same procedure, get all the way to here, and then just chuck equals 0 on each of these. Who knows how to solve that? Or even just what's the answer, and we can go from there.
The answer is -1.
Yep, -1. Do you want to have a go at trying to explain why, or should I?
So we're just like cancelling out both sides. So
yeah,
cube root 0, which is just 0, and then moving subtracting 1 from both sides. It's just -1.
Yeah, cube root and then -1. That's it. There's an entire chapter dedicated to getting you to go from this answer to here. I don't know how they made a whole chapter for it, but more practice is more practice, so really can't complain about that. It's a pretty long procedure, right? If we look at how much we actually wrote here, it was find our factors, test them, compare. You probably wouldn't write this here. You'd probably just go straight to -1 equals -b, so we could save a bit of space there. You wouldn't really need to write that, or this. You would just go straight to x plus 1. This you kind of have to do. This, yeah. So you can see how much work and writing goes into solving these, which is, again, just trying to reinforce the reason why these are kind of rare to show up, let alone with the so-called rational root theorem, which I think now that it seems like we're all fairly familiar with the procedure here. What I will do is touch on rational root theorem, and you'll start to appreciate a bit of why this makes things like exponentially worse. Okay, so back to the screen share. Rational root theorem, what's that all about? It's literally just there for polynomials that have a leading coefficient other than 1. So this one has 2, for instance, 2x cubed. What you have to do there is, instead of just looking at the factors of the last term, you're now also looking at the factors of the first term. I don't know why they've flipped the order of the B and the A, but essentially the factors of this are going to be, where is it? Oh, it's down here actually. The factors of this one are going to be in the B spot, and the factors of this one are going to go into the A spot. So what that ends up meaning is not only are you subbing in integers, but now you're also testing fractions as well. So if you take the list of possibilities here, this one's, I guess, not too bad, but it goes from just being plus minus 5, plus minus 1, so 4 options, to now adding plus minus 3 as fractions to each of those as well. There's still plus minus 1 here, which is why you can still test integers, but like now you've also got the fractions as well to test, and it just sort of blows everything up. There's nothing too pleasant about doing this. So it's an extra layer of just guess and check, which is why they don't really do it. Practice it if you feel like, just to test yourself, but seems a bit ridiculous to have a look at here. So you'll notice that anytime they say rational root theorem, there's always a coefficient that's not 1 at the front, which brings up an important question as to like, hey, why is it in here? Like, they're not saying use rational root theorem here, but these still have like 4s and 2s and 6s. What are we doing there? I didn't cover it in this lesson because this lesson was supposed to be just factor and remainder theorem. What they're referring to is, where is it? Are they going to show me grouping, or am I just going to have to explain it? Come on. Really? All right, cool. It's grouping method. So to briefly discuss what's going on there, you're effectively looking for ratios between the terms. And what I mean by that is you got your x cubed and x squared have what I call a 2 to 1 ratio. You've got a 2 here and a 1 here. It's a 2 to 1 comparison. this also has a 2-to-1 ratio. The leading one is 2, the following one is 1. Why does that matter? We can do a bit of factorization magic to make things look a bit easier. So what I'm going to do is write out this in the handwritten notes section. 2x cubed plus x squared minus 2x minus 1. What you do when you identify a ratio like this is you look at the leading terms there and you take as much out of it as you can. So in this case, x squared. You take x squared out of this, you got 2x plus 1 left over. You've also got this minus 2x minus 1 over here. And what you start to recognize is, hang on a minute, this is kind of close. Minus 2x minus 1 and plus 2x plus 1. If all I do is take a coefficient of 1 out of that, I now have x squared 2x plus 1 minus bracket 2x plus 1. Alright, that's just me taking the negative out of both and distributing it, well, I guess factorizing it is the key term there. We have now identified another set of factors that we can take out. So I'll put a little, just to make it easier to understand like why we can do this, I'm going to pretend there's a little a at the front here. We've got x squared that has this coefficient. We've got a that has this coefficient. Since they have the same, they can be taken out the front. 2x plus 1, then you're left with, in this case, you'd have x squared and you'd have minus a. Now, in this case, our a is 1, so we're just going to have 2x plus 1, x squared minus 1. And that's almost as factorized as it can be. This can go a bit further, but point being was to show the grouping method there, which you might be familiar with. It gets touched on a couple of times, but then I almost feel like there's a dip in year 10 where it just kind of gets abandoned. Was that new to anyone, or is that like good enough what I've explained there? Cool. Yeah, so that's kind of what I was mentioning earlier, which is you might not need to use factor theorem. It'll always work if there is one, but there's also other potentially easier methods if you can use these little techniques. Same thing sort of goes for like sum and difference of cubes. You can use that, although that's also about as rare as rational root theorem. There's an equation for it. If you want to learn it, it's there, but again, just make sure your teacher's actually teaching it, because I've never needed to use any of these in an exam, and I've done basically all of them. So that'll be a if your teacher is doing it scenario once again. What else is in this chapter? Now it gets into some of the more stranger questions. Just trying to think if we should... I'm going to quickly scan 6D, just in case there's anything in there that needs to be looked at. No, okay, it's literally just all solve for 0. Cool, we've already had a look on that then. Awesome, we can focus on the fun stuff then. Or the more involved stuff, we should say. Okay, question 10 here. So find the values of a and b, and therefore factorize p of x. So we got our a, we got our b there. So now there's 2 coefficients in this polynomial, not just 1. But we're also given more information. We're told that our polynomial is divisible by x minus 1 and x plus 3. I haven't done an example in my notes for this specifically, but the concepts that matter the most have definitely been explored so far. Let's see if we can now apply them. I'll let you guys have a moment to think as I start writing it out. It'll be similar to, what's the last couple of questions we did? Similar to doing stuff like the question 4. Yeah, it's question 4, question 3, that sort of stuff, where it's similar to, where you want to essentially solve for a variable such that terms are factors. Very similar starting point, anyway.
Would we do the rational theorem with the -1 and then sub in +1? And then
Yep. So that'll be, you got P of 1 by doing the remainder theorem on this one, yeah?
remainder theorem, yeah. And then you get an equation, and then you do the same, but do P of -3 for a second equation?
Yeah, that'll be exactly right. So we're creating our two equations by using two sets of remainder theorem, factor theorem, however you want to say it. Because they are factors, that does matter in how we create our equation. But yeah, I mean, the initial statement would just be sub in, so x cubed, so that's 1, plus a minus 1 plus b. Should probably leave some room here. P of 1, 1 minus 1 cancels. P of 1 is therefore a plus b. Before I write the next one, is there anything we should modify about what's written here so far? While you think, I'll write out the other one as well.
For our first equation, is a plus b going to equal 0 now?
Yeah, that's right.
Okay.
So because they're factors, we can actually say, hey, we can get the other side of this this equation. Same thing over here, right? They're both factors, so they should both equal 0. In essence, the remainder is 0. So that makes life a lot easier because now what we have are equations that both have two unknowns in them, and we have two of them. This should ring a bell from some other aspects of methods. What do we do in these sorts of circumstances?
Simultaneous equations?
Yeah, simultaneous, precisely. We have, well, whatever method we want here. You could do a elimination, you could do a substitution. Elimination, I'm seeing, the b's could cancel if you do equation 1 minus equation 2, or the other way around. You could do the substitution, which everyone tends to default to, which would be something like a equals -b, and then just replacing a with -b, or the other way around. That seems to be what most people's preference is, so I guess we'll just do that. So as long as I've written out my equation correctly, I guess we'll find out soon enough if this is going to work out. Plus 9, but a is now -b, so it's now minus 9b plus b equals 0. Minus 8b is equal to 24. So we get to 24, so b equals -3. And then a is the negative of that, so a equals 3. Well, simultaneous equation was solved. I can't imagine why that wouldn't be right. Looks solid to me. So we got b is -3, a is 3. Is that what was asked? So it says find the values a and b and factorize. So we got our first mark, maybe 2 marks to get to there. How many would that be actually? 1 mark for setting up the equations, 1 for getting the result. Sounds about right there. But it does say to actually now use that to factorize. We could do it. It'll take a while. I'm happy if you guys can just tell me what we would do from here to now factorize.
Well, now we can write the new equation with what we got for a and b.
Yes, you'd have your new cubic f of x with the new a and b stuff, which is good. What do we now do once we have that new f of x? Well, I guess p of x in this case.
We look at our last term, which was the -3, and find the factors that can go in to then divide.
You could do that. Yeah, that will work. There is actually enough information here to save you a bit of time there. I'll let you revisit the question and see if you can spot a little shortcut. It'll save you a bit of time. Think about why we're subbing in values. Like, what's the end goal?
To find what it's divisible by, but we've already been told.
Yeah, we've already been told. That's it. So because I've already been told these are the factors, we don't actually need to go find them anymore. They're already there for us. So you can actually just pick whichever one you want to divide by. You could do, this is what I was saying a bit before, which was you can actually get multiple hits out of the factor theorem. You only need one because, well, I wouldn't want to be doing a polynomial division twice. That kind of sucks. So you pick whichever one seems easiest, probably x minus 1 seems the easiest there. You do your whole division, get your quadratic, and then, well, if the quadratic can be... Actually, I'm curious just to see, based on your understanding of things, when we get a quadratic out of this, will that quadratic be factorizable based on what you're seeing here? You'll never have to answer this in a real thing, but it's nice for understanding. When we do our polynomial division, we'll get a quadratic. Can that quadratic be factorized? Or is it guaranteed to be able to be factorized? That right there is all the information you need in that box to answer that question.
Yes, it will be able to, because they're our two factors.
That's it. There's two linear factors. So if there was also a quadratic, expanding that all the way out would actually get us to a power of 4, a quartic. This is a power of 3. The only other thing could be linear. So whichever one you pick will get you the quadratic. This, whatever the other one would be, would therefore be the other linear factor that makes up the cubic. Nice. You'll never have to answer that in an exam, but it's really good to really be able to understand based on what you've got. You can make some certain assumptions, and although this in particular might not show up on an exam, what you'll get in your exam, especially the tech active extended response, will be something you've never seen before, guaranteed. They'll just chuck, I don't know, they'll chuck a circular function into an exponential and chuck a bunch of ABCs in there, and they'll be like, hey, answer a certain question off of it. And you'll have to be able to use little techniques like this and little understanding hacks to be like, okay, what is this function actually going to do? And what are the assumptions that I can make about it? And that kind of narrows your thinking into a particular way and makes solving those questions not impossible anymore. So yeah, that's about it here. That's everything that was worth covering for today. So pace was pretty nice. Maybe question 12 and question 11 are definitely different than what we had a look at, but hopefully with everything we've discussed, those should still be solvable now. Yeah, I'll stick around if you guys have any more further quick clarifications, but otherwise, yeah, we've made time. Thanks so much.
Perfect, thank you.